Hey everyone, welcome to the Proof of Solvency presentation as part of the Navigators proposal. Today we are joined by Utkarsh, who will be presenting. Thank you, Utkarsh, for joining. Over to you.
Yes. Okay. I think it is visible.
Yeah, it's showing up. Yep.
Okay. Okay. Let me just drag this off. Yeah. Okay, guys. So, good evening, everyone. I am Utkarsh, and today I will be showing you guys the endpoint presentation of proof of solvency. So, what are proof of solvencies? If you guys saw the midpoint presentation, you guys must know that proof of solvencies is a cryptographic protocol that helps financial institutions or custodians verify that their assets, which they demand from users, they actually have them and they are not spending off in some other way. And recently, I think many of you must be aware of the Bybit hack. And whenever such hacks happen for such a large amount of money, there's always a question. There's always a question that whether the exchange did have enough money. And from the past, we have seen like FTX. FTX was insolvable, and if they had a proof of solvency scheme in place, they would not. They would basically be caught way much earlier, and people would have lost way less money. So yeah. So proof of solvencies are generally made of two separate proofs, which are proof of liabilities and proof of assets. So proof of liabilities is a cryptographic protocol such that we commit to the total number of liabilities of the custodian in a hiding way and in a binding way. So it can be sort of a Peterson commitment or anything else. I'll talk about how the general approach of proof of solvency works later. And with proof of liabilities, two we mainly want 2 points such that failure of probability is low. Now, as by design, these protocols are user custodian interaction dependent. Like there is no research out there, nor there is any platform that have a proof of liability protocol that basically verifies every person's liability on their own. So there is some sort of interaction, and but my task here was to basically make the basically make it easier for users to verify these proof of liabilities on their own in a very demanding UI way. And so basically that's all. And proof of assets is similar, that we want such on-chain assets that the centralized exchange or custodian claims to have, but they do not have. And obviously, with these proof of assets, we also need a cryptographic commitment to the amount of asset that the custodian actually owns, and it should not reveal the amount of assets to be zero knowledge. Now, a general approach towards these proof of solvencies is such that we first establish the liabilities such that the custodian commit to the liabilities through some sort of an accumulator scheme. This can be a Merkle tree accumulator, or let's say RSA accumulator. There has been recent research about RSA-based accumulator schemes for proof of liabilities. Proof of assets demonstrate the control of sufficient assets through non-collusive address verification. That is, if two exchanges basically decide to share some private key, so they basically share an address, they all put funds in that address. It's not really what they claim to be, is that they have your funds, but they are exchanging the funds with another exchange, and they can basically commit to a larger amount of asset value than they have. And now compare these assets to liabilities in some sort of a zero knowledge way. And in our case, it was some sort of circuit. And then repeat this proof of solvency protocol at regular intervals. Yeah. Yep. So some other implementation of proof of solvency, which I could find, is Summa. Now, Summa was implementation back in what we say 2022. I think, or maybe even way back, by privacy and scaling exploration. And the main challenges that Summa had was the accumulator scheme it used was basically plain. So the centralized exchange had to reveal the amount of assets it has under control and the amount of liability it has under him. So it was not a privacy preserving protocol. And there has been many academic research. The main one reaching back to provisions, which happened after the Mt. Gox hack, where the Bitcoin, where 700k Bitcoin now worth I don't know how much zeros amount of money got lost, and yeah. So the one of the main reasons which Suma did not work on was proof of assets, because Ethereum, by what we say by design, does not allow for a plume nullifier scheme. Now, plume nullifiers are not a standard in Ethereum, but they are a standard in Mina. So Mina by design have a better what we say proof of assets protocol. Because the plume nullifier scheme basically removes all the what we say all the chances there are for two sets to collide. Now the protocol flow, as the image here is a little I will go into this. Okay. So the protocol flow goes something like this. So the custodian basically comes to our platform. He registers first to our platform. So in my sort of design, I'll first show you guys this, is that we are sort of an accumulator. So basically, because you as a crypto, let's say investor, you will not have a account on a single exchange. You will obviously have multiple exchanges, and it will be a pain to basically go to every different exchange and have sort of this verify their own, and it will be hard to keep track of. So at net zero, what I thought is, should we basically be an aggregator so that we can onboard centralized exchanges to our platform and allow for this better user experience towards these proof of solvencies. Now, do you think this is centralized? No, because we don't really keep any data. We are just an aggregator and all. And in future versions, I thought of porting this to ProtoKit, because ProtoKit fits the case here. But for some reasons, I got that idea very late and I did not implement it. But we can keep that in the future. And ProtoKit basically now, as a sequencer, have this finality for Mina 11 also. So it keeps sort of decentralization and at faster speeds. So the custodian basically comes to a platform, registers, have a whole setup, and all the setup is very easy. For me, it is around 10 commands in the command line and running 2 scripts. So 10 is, I think, a far stretch, but yeah. And so a user basically then deploys a script every round. It can be found in script / start round.sh. And what script lands, what it does is it basically builds the Merkle tree, the Merkle sum tree. Now, the Merkle sum tree in our protocol is inspired by Dapol Plus, which was a paper back in 2021, which had this generalized proof of liability scheme. And in Dapol Plus, by nature, what they have is they have this hiding commitment, and this hiding commitment and a root hash which is hiding. So basically, it's a full-on privacy preserving scheme. And so basically the flow goes like this. Once the sex has done all his things, he publishes, or it publishes, some parameters on chain. Now these parameters are public, like the root of the tree and some public parameters through which you derive your position in the tree. The liability zcap verifies this. Whenever the users come to Net0 UI, let's say he wants to verify the, let's say for exchange custodian A, he will demand him to send the rain check proof. Rain check proof basically is a recursive proof that ensures that at every point of the liability, at the liability level, the liability committed amount is greater than 0. So because you can imagine, as we are looking in a finite field, a user can basically commit to a larger amount, and it can then commit to a smaller amount through the field modulus. Or it can happen other way. The sex can collude, and what it can do is it can add a a padding node with a negative amount of money, and then commit to a larger amount. So through rain check proofs, we basically mitigate all this and ensure that every liability committed is greater than 0. Now the user then takes this rain check proof and witness and generates zero knowledge way. He also inputs his asset value, and this asset value is basically, let's say he keeps a CSV, or he keeps what we say an Excel sheet, or basically he goes to the centralized exchange UI and see what values he got, and is that what he really has. He inputs into the UI, and then we generate a zero knowledge proof in the browser itself, and then submit it to the liabilities verifier ZK app, where we verify this what we say the zero knowledge proof that he was included in this building of liabilities commitment. So basically, in simpler words, that his amount of money he has is in the liabilities commitment that the centralized exchange claims to be. Now, for proof of asset protocol, the what to say the custodian basically generates a zero knowledge proof of asset through a simple summing sort of. So basically, what we do is we commit to a larger array. Let's say I have 10 addresses in control, and so we commit to 20 addresses on chain, and we give that as a public input to our circuit. So basically, everyone can verify such that the addresses and the balances map that is given as the user input, as the custodian input, is correct. So basically, this is just for because if we give the addresses as private input, then it will be there will be no way for us to verify that the balances that the custodian claims for an address to have is actually the balance he has. And yeah, so and he basically proves this, that the address that he owns it through a nullifier scheme, namely Plume. And then when this sort of
Yeah, I'm sorry to interrupt you. I just while you were talking about addresses, I also wanted to understand: is this applying to like one single protocol, basically checking of the balances? Is it like applicable only to Mina addresses, or is this applicable to any addresses?
So the the idea remains same, that we need a Plume what we say signature, and I tried having a Plume signature for other foreign curves on Mina, but there is no Poseidon hash to foreign curve function. So it basically makes it at cryptographic level more difficult to have. But if we can have that implementation, then we can verify foreign curves also.
Okay, all right, thank you.
Okay, so the custodian basically then generates proof of solvencies. The proof of solvencies, he inputs the amount, what we say, what liabilities he has, what assets he has, and the public commitments from the blockchain into the circuit, and generates zero knowledge way that the difference of the public commitments, that is a Poseidon commitment, if I did not mention it. So they are basically homomorphic in nature. So the difference between those two is actually equal to the asset minus liability value, and both the values are positive. So this is sort of the protocol flow, and let's get into the demo. Okay, so this is sort of a UI screen that you come across, and when you click get started, you go to this login page, and it's so currently the login, I have some sort of a backdoor in login to allow basically users that were included in the protocol itself to have to basically log in. So I will log in through, let's say this, and let's send OTP, so it instant, and whatever I do, I can verify. And let's say, so here you select your custodians. Basically, we want another level of verification, that there can be a malicious user which basically generates this fake proof of solvencies for let's say whatever reasons he have, and we basically also want to mitigate that. So for this reasons, we have what we say a dispute resolution, that let's say you claim to be a part of the centralized exchange, and let's say your proof of solvencies fails. So what do you do now? I mean, the only way, we cannot have a cryptographic way of this. The only way we can have is have a basically centralized exchange. From the UI, the user raises a dispute ticket, and the ticket gets verified at the centralized exchange. And yeah, so, and for dispute resolution, the only way to have some sort of what we say backing is through legal mitigations or something like that. And I think we can have a terms or conditions in place to basically basically make fake proof of solvency is more difficult to have. So let's say I select these exchange now. Obviously, in what we say in this, so in this in demo, we have multiple exchanges, and everyone is part of every exchange. Now you see too many things here, and what you can do is you can basically add some assets and what we say values to your exchange. So let's say you are a user, David Jones 20, and you come and let's say you are you want to verify your proof of solvency. So basically, you come here and you select the exchange you want to verify for. Let's say we verify over the crypto exchange. Oh. Hmm.
You've got the debug curse, unfortunately.
Okay. So the problem basically is that the APIs are hosted on a HTTPS server, and this is running on the local host, and I cannot have any sort of login or cookie setting in it.
Gotcha.
So the time by you try it, it will be much better experience. So I will select the cryptographic exchange. Let's say I have asset 1, cryptographic exchange, asset 2, and cryptographic exchange, asset 3. So basically, I had some dummy data in place. You can find it on the GitHub itself. I will link, I think, in docs. So okay, so let me tell you about docs later. First, let me go. And I will now look at my data.csv that I have. And
while you're doing that, is collateral what you have deposited and the debt your PNL? Is that how you're kind of imagining this?
That is basically what we say. Let's say you leverage some ETH for USDC and also But in the end, it does not matter for the protocol because you sum the liabilities, and let's say even if you have negative balance, we rain check the positive liabilities. So in let's say development or in beta, we do not have this sort of every token is 1 rupees basically. So we can do a simple check, but let's say if when we are in production, we multiply the asset value into its what is actual prices. So basically every calculation is done in dollar. And even if you have negative balances, every user should have positive balances. That is a given. So we range check the total value and ensure that you have greater than 0 in the range proof. So I will do 0. 11,600. 4651. So the data generation for this was very simple. I did a Python simple script, and I mean, in futures or in let's say in the documentation, I can have complex examples with negative balances also, if that is something was there. Okay, so you save these sort of crypto exchange assets, and the logo is actually not working. So sorry for that. Now I will show you in the terminal because in the terminal I have range check whatever we do step by step. So in the terminal, I'm saying console. So basically, you get this sort of from the backend of the what we say custodian. You get this sort of Merkle witness and proofs. You get your master secret, your blinding secret, and user secret that are part of the tree. So basically, these params are basically a key derivation function. So a key derivation function basically whatever account ID you have maps to a larger set. So we do not have the sort of close account IDs, and let's say you can guess a user's account ID and maybe some angle of attack from there. So KDF basically prevents that. So a key derivation function does this. And one caveat is I use the node crypto library, and the KDF function HKDF sync in that is not present in the web version. There were some workarounds, but apparently the values are not the same. Like KDF of the same value in the node version and browser version are not same. So maybe for the beta, I think it will work if I ask the backend directly for the blinding factors. But what the liabilities once the liabilities protocol happen, so there are two public parameters, salt B and salt S, and through the master secret that the exchange gave you, you can compute these parameters yourself. So basically, you can compute the blinding factor and the user secret yourself. And basically, one more layer of verification that the exchange did not collude in any way there also. Like it did not give you another KDF of some other person in the tree, and you basically got a fake verification. So we have a rain check program. So the contracts basically rely on three things: a rain check program and an inclusion proof program that is verified on chain. So yeah. and the compilation times are slow. But I think this is because I'm running. I have opened many browsers on my window. I think it will be better if you have some sort of less browsers. So while that happens, I think I can jump into some code if you guys are interested in that.
Yeah, please carry on.
Okay. I think it is done.
I mean, I might have a question in the meantime.
Yeah.
Uh, I know you
So
mentioned like everything is kind of marked, or like all assets and liabilities are converted to USD uh,
yeah, yeah.
and checked. Uh, I'm trying to understand because as someone who has assets on an exchange, these values keep changing, right? Uh, and
Mm.
when the proof of assets is generated by the exchange, it will be marked to a different value
So
rather. Yeah, so I
uh,
think you're getting understanding the question, and like how are these
yeah.
values compared
So what you
because
are
they're at
asked,
different
what you
points
are
of
basically saying is there a timestamp you basically put for this, and yes, there is, and for our reasons, I could not find otherwise something else. Uh, let's say we can have a public contract which basically publishes these timestamps, or we have something like every exchange must come together and generate this proof at this particular point of time.
time.
So this sort of things, they are, and these are also depending on exchange to exchange. Maybe you have a larger exchange and you don't want to spend that much compute power, and you would generate seldom proof of solvency, seldom this protocol. But since you have so much large throughput and you would not like basically want this
Sure,
cost incurring to you, because it's sort of an extra cost. Like
sure.
users already trust you, and why would you have these sort of proof of solvencies? And let's say if you are shorter exchange, you can generate this seldom. So this basically depends on the exchange we are onboarding, and we can ask them and have some sort of mutual agreement between users and exchange to basically add this timestamp. So yeah,
Mhm.
everything will at a particular timestamp or at
Okay.
a particular block number, you can say.
Yeah, and do you know currently what is like I guess what most proof of solvency solutions do? Are they like doing like once a day or once every
So
month?
uh, they, I don't think so there is anything like this. The only thing is Binance,
Hmm.
and what Binance really does is it does an exhaustive Merkle tree. Basically, it verifies that you are included in a Merkle tree in a circuit itself.
Hmm.
So because Binance uses Ganark, and their low-level APIs are, they have some low-level APIs like the lookup tables or etc. That was possible there, but in O1JS, I had some constraints regarding that, and we could not do that. And other solvencies, I don't think so. There is a platform like a
Hmm.
dedicated platform provider for this proof of solvencies itself. So I think there is a lot of market capitalization there, if you can
Hmm.
understand what I'm saying.
Hmm.
So, and yeah, so there is an, at every epoch, let's say if we go to Binance proof of solvency, so basically, oh, so you can, this is a, the as you can see, the exchanges amounts are already in clear public, because whenever you go on a, what we say, Explorer, you can already see if this address is owned by Binance or not.
Hmm.
So I think this is a nice to have for, let's say, a private exchange which wants to happen, and they obviously would not want a private proof of reserves in here, or let's say a derivatives platform. They do not want to reveal the public addresses. That is what we can have there, and I think proof ZK Merkle. Basically, from the dashboard, you can go to. I cannot find. Hmm. I'm coming for just with articles. So basically, there is a dashboard, and what
Mhm.
they basically do is they hand you the binary, they
Mhm.
hand you everything else. They say you generate this on your own, and then you can verify it on chain. Is
All
what
right.
they basically.
Hmm. Okay. Uh, I mean, I might have like just one very quick question,
Yeah.
and then I'll let you continue. So from so from the exchange's perspective, it's easier to say, hey, I've created a proof on this particular timestamp. But for a user who wants to verify, his, because again, like I said, his collateral and depths are constantly changing, and if an exchange publishes a proof for like 12 a.m. Um, and let's say is there like anything which the exchange needs to provide on top so the user can also like
Hmm.
uh, get the exact data of his debt and collateral to have it verified? Because it seems like the other part of the equation and the user might need to do a lot of the legwork for this.
I think for this we would have to do some sort of time, because there has to be a
Yeah.
timestamp at both of the user and the agree. Either the user is very conscious and he always go to 12 a.m. in the exchange and sees his value and copies it down. We love those users at Net Zero, and because and other than that, I think the exchange would have a specific page as per se, and actually we can provide that in admin UI sort of stuff. So basically,
Yeah.
we can do an admin UI that basically displays these assets value. And let's say you basically did not do any. So I did not show the dispute button. Basically, you can raise a dispute here. You can provide the transaction URL, which or the whatever transcript you have.
Hmm.
That's fake. You can provide the asset value that you put, and you provide the description that you have.
Hmm.
So maybe through some sort of interactive way, we can
Yeah.
solve this problem. uh, yeah,
Yeah.
that's
I think
basically.
a read-only API to an exchange would also be nice. So if I have like, I think I'm instead of manual, I mean, of course, these are like future enhancements you can think about. But just having like a read-only API key to an exchange where your assets are there, which could potentially just pull, like, query it and pull it, and then you would have, like everything in black and white. And I also think that would be, I don't know if they do it by timestamp, like a historical breakdown of your assets, but it might be something that might make
There
things.
must be sort of transaction history there
Yeah.
also. I mean,
Yeah.
I don't think so. So Binance actually, basically Binance, what it does is it every action the users take, it records that action.
Hmm.
It generates a tree that
Okay.
your action reflected the balance changes in
Hmm.
balance. So it basically a user create operation, whatever the
Hmm.
operation is, and it tracks every operation it has. So in that way, we are doing a less exhaustive, you can say,
Hmm.
search, but that comes at a what we say a trade-off at a higher generation. And Binance also does have a lot of money, and let's say smaller exchanges do not
Hmm.
want to spend that capital again from a business point of perspective. I mean,
Hmm.
you might be spending what say hundred thousands of dollars, what you say, generating proofs, and no one is there to verify it. And then why would you want to do this? So there is
Hmm.
sort of what we say resistance from both sides, and especially exchange sides, because they would have to basically put a compelling argument to their accountants and all for having this sort of proof. And I think the only way we can have is through awareness and maybe running social media campaigns or
Hmm.
something like that. Because well, I mean, we do have a lot of examples of this. Like, why do we need this? And I think there are many users, and most probably the users which have the most amount of money, that are unaware of such zero knowledge protocols. So I think with enough awareness, we can have sort of this, have the exchange also come on, and have a mutual solution between the two. And about the API, you said read only. I don't think so. I mean, I thought of basically making database adapters, but then
Hmm.
again, I thought, why would a exchange give a database to a unknown third party? I mean, it's not like we are what we say uh, hosted in plain sight. We do have a backend where we do this sort of communication between the exchange and the user. So I mean that does not make a sense. That does not make sense from privacy standpoint also. I think the only way we can have this is sort of do an admin UI, and an admin UI basically publish a list of, let's say this, exchanges and list of assets or timestamps with the user. Or another thing we can have, I mean, one thing that I thought of was a very good use case of ZK email here. So with ZK email, you can basically every exchange basically takes your email, and like Binance does email verification and all. So with ZK email, you can prove in zero knowledge that you are part of the exchange, and we would not have to do this some sort of what we say publishing the asset. And in the exchange side also, it will be very easy to verify that you are actually part of the exchange.
Gotcha. Yeah, no, everything makes sense. Please carry on. Thank you for the explanation.
Yeah. So I think I'll do a code walkthrough of the contracts and the, let's say, the what we say, the contracts and the circuits. So, and let me move this to another screen. So moving things are a difficult task. Yeah. Okay. Okay, I was sharing tab, I think. Oh my God.
Yeah, we can see like the 3 tabs. So maybe just a window was shared.
Okay. Got it. So you can see these 3 tabs, right?
Yeah, so slide dev, Excel draw, and we know how many Google messages are in your inbox.
Okay. So, yeah, so let me share this. Let me share the screen again with the code itself. That's fine. Yep. So this was sort of the asset.data from which I took the values from. As you can see, 50, 90, 1160 is what I inputted in the UI itself. And so basically the directory structure is something like this. So I do not have comments in place right now. Maybe I'll do a comment run in place, but I think everything is very self-explanatory. Like there is no outstandish optimization I did and that I'm a genius coder. So the tree core basically is the core tree structure that we make of the accumulator. And in this, the main function is this node merge function, which you can see here. So a node merge function basically generates the sort of, so node merge function basically merges to node. Now this is out of circuit thing, and it basically checks a merge the rain check proof as well. So the merge rain check proof basically takes in the left proof, the right proof, which are self proof because we have a lower leaf level proof also, and we basically merge those 2 proofs, verify both of them, and we merge the new sum. Okay, so that's that. And the tree builder is very simple. Like there is no simple like how you would build a binary tree. So basically you would start from the leaves, you pad, you basically, so one more thing we want to have is have some sort of sparsity to how actually amount of leaf nodes you have for each user versus how many padding nodes you have. So a padding node is something, because let's say you do not have a padding node, then you would have to basically, if a sibling is not present for a user, we would have to fill it some sort of way. So padding node prevents that sort of stuff. And a padding node also to provide an extra layer, because there is no way for you to, as a person seeing the tree with just the commitments, to know which type of node it is. Is it a user node or is it a padding node? And the x coordinate through which the leaf generator they go randomly for now. But what I was thinking was having an ORAM based approach in place, but that level of computation overhead I think was too much for what it offered. So a random arrangement every time the tree is generated, because then it will prevent some sort of access pattern attacks, which I talked last time also, is because let's say you are a attacker and you want to see who is your sibling in the tree, and let's say we keep the same tree. So whenever you, let's say you query the proofs every 30 seconds or so. Now every 30 seconds, so you would have an idea that okay, the user beside me, his
Mhm.
balances are changing or not through just the change in the commitment value. Because even though the commitment is zero knowledge, the value must change, and that must mean the balance has changed. If the balance has changed, that must mean some sort of on-chain transaction must have happened, and that on-chain transaction would be reflected in the network blockchain, and you could basically link two and two together to have
Mhm.
some sort of uh, take out the zero knowledge thing in this. And yep. So the proof of reserves, the POR circuit is actually a bad name for this because it does both proof of reserves and proof of solvencies. So as I said, the proof of reserves protocol basically takes in the proof of assets public input, which takes in the selector array commitment. So the basic idea was, because this process is slow, is that the user, the centralized exchange, will commit to the asset value and etc. Uh, let's say some time before generating this proof, and have this proof then verify on chain. Basically, the reason why ZK is used is off chain computation versus some trace of that off chain computation into the circuit, the selector array and whatnot, and then you would generate basically a async process for submitting the proofs. So the proof of public asset input basically has the selector array commitment, which is on the public contract as well. It has these public addresses. Now, one thing to note is that number of public addresses and number of actual addresses is double or some sort of threshold multiplier. Now, this is where the zero knowledge thing kicks in, that even if you have a smaller subset of assets and we want to verify that the balances that exchange put at some timestamp were the true balances that he inputted into the circuit itself. So that's why this sort of a larger address or balances array you put as public input, and you put a selector array, which basically is a boolean value if you own the address and if you do not own the address. So that also is generated in zero knowledge through a selector array program, and we basically verify the nullifier first for the public address, and then we provable dot if and all not you commit to us the selector array value. You commit to the whole array, and then you basically on the contract itself, which is the verify, and in the contract itself you assert that the public inputs to this selected array etc were correct, and that the proof is verified, and then you basically set the asset commitment, that is the public output of the proof of reserve circuit, to the on-chain asset commitment. And I think a top-down flow would be better, that I would first assume the contracts. Now, why this composable sort of, why this three contracts? I mean, this was due to the limitation of 8 field elements you can have in a contract. So because I have many public these parameter sort of these public parameters, and we want multiple of them. So I had to think of some sort of composable way. So a POL verifier is separate. This verifies proof of liabilities only. The proof of asset verifier is separate, and the proof of solvency verifier then just verifies proof of solvency through the public commitments and values on the other two contracts. So yep. So as you can see, the public asset verifier public input dot asset commitment to the circuit of proof of solvency, which you can see there. Oh, there. So everything is also published in an npm package. For let's say exchange wants to on they do not trust me and they want to use the circuit on their own, they can do that. Very easy to do, not something not a difficult task at all, and everything is again open source as well. So I don't think so forking would be anything. And the proof of solvency basically takes in the proof of solvency public inputs, which are the liabilities and asset commitment on the blockchain, the asset proof, that the proof of assets, which is generated in zero knowledge, the rain check proof, which was that the liabilities commitment in the initial tree has merged together and the liability is greater than zero. So in this circuit, we have rain check the asset value, and because in the proof of asset also we rain check the verifier, we rain check the balance that we commit to. The to add the thing we add to the total asset value, we first rain check that. So this is to basically mitigate any sort of larger balance commitments from some sort of negative numbers. So then we take the asset value, liabilities value. These are something that the exchange itself has in plain sight because they know their what amount of assets they have, now liability they have, and the blinding factors. The blinding factors are available through a basically when we generate this sort of through an interactive script, we save these sort of values in a JSON, and these values you can then pull it out of the JSON, put it in the circuit, and everything the exchange, the only thing exchange has to do every round is just run a script, nothing else, and basically prepare the asset inputs also. And then in zero knowledge, we verify that the net committed commitment of the asset is greater than what was from the what we get from the basically private inputs that we take as input. So yep, that's all. And I think in the script you can see there's a contract deploy script also. We deploy all the contracts for you. You do not have to go through the headache of deploying everything. And there's a start round script. The start round script, basically, let's say you do not have any balance changes before that, so you can load a store, because whenever I make this tree, I save the intermediate node values to a Redis DB, and the Redis DB basically acts sort of a cache through which we can pull out these witnesses or pull out this tree store, the tree structure itself, and for some sort of caching and fast mechanism, so that every time you do not have to make this whole tree whenever users ask you. Let's say you do not have any balance changes, you can just load store and start another round. And in another round, what we do in interaction scripts, you have assets interaction, and you have, I have mentioned what this script does. It takes in the JSON with the, because as the nullifier screen, the user can generate this sort of nullifier and the public key in private, and we do not take the private key as an input to the circuit. Let's say in a secure enclave, you do that. And I talked to some guys at in the Discord as well, and Ayush, who was the prime author, or the, let's say, the what we will say, the lead author on the paper of Plume, like whose idea it was, said that this is possible for cold wallets also, but there is a ledger, there's a PR in ledger that has still open, and they do not accept it. So for cold wallets, I don't think so there is any way right now, rather than in the private key generating this sort of, you are generating some sort of in a secure way. And the only reason I did not do this through a UI is because something like the safe hack happened, because they hacked the UI itself. So I think it's better for us to move this sort of processes to a more backend and developer friendly rather than a user and a founder friendly, because at least the developer will have some sort of info on what params we are doing, if that makes sense. Yeah. So that's what we do in this nullifiers. We pass the address, we pass the files that the exchange gave us, and we create a selector array, and we verify the transaction on chain. Yeah. So the same thing we do in the asset verifier itself, and we create the tree, we set the contracts, whatever public commitments we have to set. Like we set, wait, let me see. We set the root and params on chain in the transaction, and we deploy the transaction. And if in the load and store contract, we directly load the thing from the DB itself. And in the solvency routine, we assume that the previous two steps have been done, and then you come to this, and that's what the script does itself. Is it first goes through the liabilities protocol, it builds the tree, it waits, it generates the asset protocol, it then waits for the transaction to happen on chain, whatever things to reflect, and then it verifies the solvency, proof of solvency on chain. So everything all in all should take about half an hour. So ideally you should be able to generate this every half an hour. But whatever the compute costs are there, I will not put it like this is a magical protocol. you have to put some assets, but everything comes at a cost. You are trading the user's trust for some sort of money. I think that will be longer a benefit to the exchange itself in the longer run. Yeah, so this is the main thing. And uh, yes, so in the UI itself, I'll show you the UI code also. Let me close this. And okay, so in the UI code itself, what we did was we handle generate and verify. This is the main function that when you click generate and verify your for the exchange happens. It basically compiles all the contracts and all. It pulls something from the exchange, and the main struct is that everything happens on the user side also. Like all these value of the backend URL liabilities, we do not keep anything. We do not keep the addresses and all. We do not keep the transaction you have or the assets or the amount of assets you have under us. These all are happened through the backend in the code that I show you. There is a mini fastpass server there also, and the only purpose that server serves is to answer the sort of the pre-queries that it gets from the user. So we query the path from the user from the get inclusion proofs URL from the exchanges backend. We fetch the liability ZK app address, and all in all, we compute the balances from the table entries, and then we generate the proof. We verify the proof on chain. And yep, we throw any errors if we have. And I think we can see the the transaction I sent in the demo to the block explorer. And let me this here. So this was the latest transaction on this is the proof of solvency contract we have in play, the proof of liabilities contract. And so because this address is the deployer of everything, you can see many transactions here. This is sort of the owner of the address. I mean, so yeah. So in this transaction, we basically receive updates. Okay, one and 24 minutes ago. Yeah. So this was the transaction that I did. Yep. So this is all from my side. If you guys have any questions, please feel free.
Yeah, you have been very busy with Kirsch. Thank you for walking us through the presentation and all the work you've done. It's very impressive. Thank you for building. I'm just going to look at the audience, and if you have any questions, please feel free to come on the stage or put them in the chat. Very happy to read them out. I don't think there is anything. So once again, thank you so much for your presentation. Really excited to see this hosted, and then like you'll get some users to try it out and go from there.
For sure. I think together, like this is a very fitting use case for solvencies, and I basically urge everyone to read about them. They are very interesting. There is years of research behind this now, and there is always this what we say fight for this. What you said, instant time proof solvencies. There has been many tries, and yep, I think this is something that is very what we say something that is in the need of the hour in the upcoming thing we have as the crypto adoption increases. Obviously, the centralized exchanges, we go to them because we do not want the scheme management stuff, and to have this sort of tension-free, what we say stress-free environment that you can trade your meme coins in. You want to see that your assets are actually.
Absolutely.
Yeah.
So thank you all for joining. Thank you, Utkarsh. We'll see you.
Thank you.
Take care.